Hello, welcome to Unit 6. So we are cranking through this year. We're going to do states of matter and gas laws this unit, and next unit will be solutions, and the final unit of the year will be acids and bases. So we only have 3 left. So today we're going to start off with talking about kinetic molecular theory. So your success indicators, obviously, here, just kind of talking about gas particles and their motion. So with kinetic molecular theory, it's based on the idea that particles are always in motion, okay? And we know that. You guys learned that in physical science, that even solids, the particles are still vibrating next to each other. So every particle is always in motion. The only time it would not be is if it reached absolute zero, and no one has ever been able to achieve that. So all particles that exist anywhere are all in motion. So this model is going to explain the behavior of an ideal gas. So an ideal gas, whenever we use that term, you'll hear real gas versus ideal gas. So ideal gas is this hypothetical gas that perfectly fits all of the assumptions of the kinetic molecular theory. Okay, so they're going to have the perfect situation. We know that that's not always true. In most cases, it's not. So we know that in real life, so a real gas would not follow all of these rules, but we're going to talk about them. Okay, so we have 5 assumptions of the kinetic molecular theory. The first assumption is that gases consist of large numbers of tiny particles that are really far apart relative to their size. Okay, so if you think about the air in the room that you're in, okay, there's millions of particles of nitrogen and oxygen and all of the things in the air around you. Okay, that could vary from place to place, but in general, you have kind of the same like hydrogen, oxygen, nitrogen, and all that. So we have very large numbers of these particles, but these particles are so small and they're moving so fast that they're actually very far apart from each other. So there's a lot of just like blank space in between these gas particles. The second assumption is that collisions between gas particles and between particles in container walls are elastic collisions. Okay, so that means that there's no net loss in kinetic energy. And so what that means is, like, think about it this way. Let's say you had a bouncy ball and you throw it at the wall as hard as you can. You know that the wall is absorbing some of that energy. You're losing a little bit of that energy to sound energy, probably a little bit of heat energy. Basically, the point being that you can throw a ball at the wall and it's not going to come back at you with exactly the same amount of force, right? Because you're losing a little bit of energy somewhere. But the kinetic molecular theory is saying that the collisions between these gas particles and when they're applying pressure to the walls of the containers, it's going to be an elastic collision. They're not losing any energy at all. Okay, so here's kind of an example of that. So this is something we talk about a little bit more in physics, but you have elastic collisions on the the left-hand side here, meaning that they're going to hit each other and they're going to just bounce off with exactly the same amount of force and energy in the opposite direction. So they're going to collide and move separately. Kinetic energy is going to be completely conserved. With an inelastic collision, the objects are going to hit each other and kind of move together after a collision. So if you think about like a fender bender. Okay, so let's say that you bump somebody's bumper in the parking lot, right? You kind of hit them. Both cars are going to kind of like move together in the same direction for a second before they come apart. That would be an inelastic collision. Okay, you're going to have kinetic energy not being conserved. So in order to fit the kinetic molecular theory and to have this ideal gas law, which we'll talk about eventually, you have to assume that all of these particles are elastic, all these particle collisions are elastic collisions, and that you're not losing any kinetic energy within these systems. The next one is that gas particles are in continuous, rapid, random motion. Okay, so therefore they can possess kinetic energy. Okay, so they have the energy of motion because these particles are always moving. So to fit that kind of ideal situation, the gas particles are never at rest. Number 4 would be that there are no forces of attraction between the gas particles. Okay, so this kind of ties in with 2 and 3, meaning that there's nothing attracting them to one another. So when they hit each other and bounce off, you're not losing any of that kinetic energy because they have no attraction. They're just bouncing and moving on. The last one is that the temperature of the gas depends on the average kinetic energy of the particles of gas. Okay, so this is mostly true in pretty much all cases unless there's some alteration done with pressure and things like that. But the temperature of a gas is going to depend on the average kinetic energy. So if you think about that, if you heat something up, like think about water, we're boiling water, we're adding heat energy to that water, it starts to move around more and more and more, and eventually it starts to evaporate. So you are adding a lot of energy to that water. Those particles in the water are gaining a ton of kinetic energy. They're moving around very quickly, and that's directly related to the temperature that you've applied. So before I move on here, if you look at these pictures, the amount of energy can also be represented by the magnitude of the arrow in diagrams. So if you see a diagram like this and you're comparing these two, here in this box you have very long arrows. What that's representing is a large amount of energy, right? So these are moving with a higher amount of energy. They're moving probably faster. This is supposed to be representing in a situation with a higher temperature. So they have large energy, high temperature, they're more spread out. In this example, you have smaller arrows, which represents less energy, and that is also correlating to a lower temperature. So you have less space between the particles because they're not moving as fast. The arrows are representing that. So the formula we're going to use for the kinetic molecular theory is this one. Kinetic energy is equal to 1/2 times mass times volume squared. Okay, or sorry, velocity. So this is our formula for kinetic molecular theory that we're going to use here. So we have kinetic energy is equal to 1/2 mass times velocity squared. Okay, so we're going to have the mass in kilograms, the kinetic energy is measured in joules, and the velocity is meters per second. We haven't worked with these terms a lot. This is more physics concepts for the thermodynamics unit, honestly, but it is directly related to chemistry. So the more energy you have in something, the more mass you might have, the faster these particles are going. That's all going to tie back into the gas properties. Okay, so how much pressure is that gas pushing? How much pressure is being created on the inside of the container that it's in? How far are these particles going to be spread apart? The temperature, volatility, and all of those things are kind of tied into this. So some other physical properties of gases. So we know that gases behave this way, and I know you guys have talked about this before in other science classes with just like the properties of gases, solids, and liquids. So we know with gases, they have no definite shape or volume, okay? They expand endlessly until they fill up the container that they're enclosed in. Okay, so if you have an example here on the right-hand side, you kind of have an area that's compressed, and then when you release that area and make it bigger, the gas is just naturally going to expand. It's going to fill it up. And that has a lot to do with the kinetic molecular theory because we're assuming that these particles are moving around randomly, very fast in all different directions. So of course they're going to spread out. Fluidity is another property of forces. So you do have attractive forces between particles, but they're very, very small. They're almost insignificant. So because of that, the particles are going to slide easily past one another. Liquids and gases are both referred to as fluid. Okay, so fluidity in this sense is not talking about like just a liquid being a fluid, but fluidity is talking about the fact that there's such a small amount of attraction between the particles that they're able to easily move past one another. Okay, the last thing here, because we're going to save fusion and diffusion for later. So the last thing to talk about here is that the physical properties of gases also include having a really low density. Okay, so again, this goes back to your kinetic molecular theory. One of those 5 assumptions is that the particles are spread out. So it's a low density. The density of a gas is going to be like 1/1000th of the same as substance as a liquid or a solid form. So if you're talking about water, right? So if you have water vapor, it's 1/1000th of the same density as like water or ice. So very low density. That just means that you have more empty space within the same substance. They're also compressible. Okay, we just talked about that. One second. All right, so the compressibility of gas particles just means that you can squeeze them together, you can decrease their volume because they're low in density, right? So these gas particles are low in density. There's a lot of empty space. So you can increase the pressure, like in this example, you can squeeze them down and you're still going to have a lot of motion. They're just going to be closer together. Last thing to talk about, which has to do a lot with the expansion of the gases, is effusion and diffusion. So gases are going to spread out and mix with one another even without being stirred. Okay, so if I lit a candle in the front of my classroom, everyone will be able to smell that candle within a few minutes probably, because it's going to diffuse across the room. It's going to mix with the other gas particles in the air, and then they get in your nose and you smell it. So what we're going to work on today is just looking at the properties of gases. So the assignment is looking at your 5 assumptions of the kinetic molecular theory, like assigning those to a situation. So you're going to look at the pictures, the diagrams that are given, and be able to identify which of those 5 pieces of the kinetic molecular theory are going to be identified there. You're also going to have some other questions that just look at the properties of gases and compared to solids and liquids. So give that a shot. It's 3 pages, but there's only like 4 things on each page, and you're just identifying them. So it's not a ton of work, but it is a good refresher on the properties of gases, liquids, and solids. Please let me know if you do have any questions, and I will talk to you guys next time.